Okay.
Hi, today we are very happy to have Anna Bonaca joining us from Harvard, and she's going to tell us about locating a dark matter subhalo or a dark matter subhalo.
Yes. Thank you so much for listening. This is one of the big questions of what the nature of dark matter is. And one of the ways of going about it is measuring what is the lowest mass dark matter subhalo that exists in nature. And in the next 45 minutes or so with live, I'm going to discuss on how we can go about searching for such dark matter subhalos. So dark matter subhalos that lack any stars or baryons altogether in the Milky Way itself. And what is going to be turn out to be really useful in such a search are actually luminous clusters of stars, such as a globular cluster here. I forget which Messier number it is, but it's a beautiful image of a globular cluster taken by the Hubble Space Telescope. And just as a brief motivation of why I want to do that, I want to illustrate how the particle nature of dark matter is encoded on the small scale structure of dark matter halos. And so this is a visualization of a cold dark matter halo of the Milky Way mass presented in a review of James Bullock and Mike Will and Colchin from a couple of years ago. And in this case, the particle mass of dark matter is something on the order of GeV. And you can see that like this massive halo is filled with small substructures. So there is a myriad of these lower mass subhalos that go or bound clumps of dark matter all the way down to Earth masses. However, if the particle mass is a little bit lower, something like in the order of keV, this is the case of so-called warm dark matter. You can see that overall the structure of this halo is similar. So this is by design because they use the same initial conditions in these two simulations. However, there's a lot fewer bound structures in the case of warm dark matter. So immediately here we see how actually measuring the sort of lowest mass of the dark matter subhalo could tell us, could distinguish between these two cases. And of course, this is a conference about fuzzy dark matter. So this is sort of on a different scale altogether. So here showing a simulation from Phil Motz, and I believe like he'll be recording a talk to be discussed on Tuesday. That shows the structure of a dark matter halo in case where the particles are very low, extremely low mass bosons on the with masses on the order of 10 to the minus 22 electron volts. And so the structure then is very different and also very transient, which doesn't really come across in this static image. But as regards to the small scale structure, like in this case, we really shouldn't have any or very few dark matter subhalos. So our goal then, or my personal goal, is to find what is the minimum mass of a dark matter subhalo that is orbiting the Milky Way. And as I hinted at on the title slide, the way we're going to go about it is using globular clusters, so clusters of stars. And the image over here was very, very nice, very complicated image of a globular cluster where like you can resolve all of the individual stars that have different colors and different brightnesses to kind of see how this how we are going to search for dark matter with such clusters of stars. We are going to do the first thing that physicists do and approximate all of that complex physics with just a point over here. So in our case, like what is really important is that this globular cluster is orbiting the Milky Way galaxy and losing its stars. So I'll start simulating this process of globular cluster orbiting the Milky Way. And for reference, the size of the Milky Way disk is shown here, and the location of the sun is the star. So since there are so many stars in the cluster itself, at some point they come close to each other and get kicked out due to two-body encounters. And so stars leaving the cluster are doing so from the two Lagrange points, one that is at lower energies than the orbit of the cluster, and one at higher energies. I'll just replay this one more time. So you can see this when the first stars start coming out, they're forming this, what we call the leading tail, and then the trailing tail are the stars lagging behind. And the reason why we are interested in this group of stars is that they're sort of just barely managing to escape the globular cluster. So which means that their orbits are still pretty similar to that of the cluster, and the structure is sort of very, very thin and kinematically cold. And since it does, so the cluster orbits in the Milky Way, and during its orbit time explores part of the volume. It also, we hope, it would retain some archaeological record of everything that it has encountered along the way. And so this is how we simulate it. This is the simulated view of a globular cluster stream. As for the real deal, here is
Anna, can I ask some basic questions?
Yeah, go ahead, please.
Is it correct that a globular cluster is sufficiently compact that for it to be tidally disrupted, it has to get fairly close to the center of Milky Way? How close does it have to get before it's tidally disrupted?
That's a great question. So, so for dwarf galaxy, that is that's the process how they get disrupted. So so dwarf galaxies are kind of slightly less dense than globular clusters, and indeed they disrupt as they come close to the galactic center, and probably the final disruption happens like in the inner 10 kiloparsecs, I would say, and the majority of stars are stripped at this pericenter when the orbit is closest to the galactic center. However, this process of globular cluster disruption, or like the main mode of it, is called evaporation. And so no matter where the globular cluster is on its orbit, along the Milky Way, some fraction of stars are going to be leaving just because they get enough of an energy to become unbound due to those two-body encounters with other stars. So,
nice.
And this indeed is due because the globular clusters are so dense. So those two-body encounters between two stars are much more common than, say, in a dwarf galaxy. Yes. So to a good approximation, I can imagine as globular cluster constantly losing mass at a constant rate as it orbits the galaxy. Yeah.
And you also mentioned the fact that the streams, when they come out of the globular cluster, is very cold. Is it fair to assume the velocity dispersion inside the stream is of the order of the velocity dispersion of the globular cluster, or is actually less?
It should be of the order of the globular cluster. Yes, it is. So I think there are like competing statements in the literature saying that as part of it is that you could imagine the older stars that have left the cluster first could start phase mixing, which would increase the velocity dispersion. Also, I think that it might, as it stretches out in sort of phase space, that the structure could become colder. So I think to the first order, yeah, you can think of the stream being the same or order as the globular cluster in terms of velocity dispersion. But in detail, like we haven't yet studied these exactly. But it's a very good point, and I will get or touch upon it really at the end of the talk, because excitingly, I think what is really motivating such theoretical studies in the future is that now we are starting to measure, starting to get precise enough velocity data on stellar streams to actually resolve the internal velocity dispersion, which is very exciting. But okay, so to move on, so this is, yeah, we talked a little bit about the velocity dispersion. But for the longest time, we really only had images of stellar streams, and sort of the poster child is the globular cluster Palomar 5, shown here at the center of the image, which is a dark blob, and which has two tidal tails emanating from it. So you can actually see where the Lagrange points are here, offset from the cluster, and then it has the leading tail towards the right, and the trailing tail towards the left. And you can see that it is like very thin, but there might be some curious changes along the tail. So it looks like it's becoming wider on this part and thinner on the other side. There also seems that the density of stars along the stream is not completely uniform. So it looks like there's like a sharp density drop after a few degrees from the cluster itself. And this is not exactly what we expect in a smooth galaxy. So the model I showed you was just having the globular cluster release stars at like a constant rate. And so what that produces is a globular cluster stream that looks kind of like this. So there are some density variations or kinks along the stream that are caused by the escape mechanism of the stars from the cluster itself. But by and large, a stream that has evolved in a smooth galaxy, such as the one we would expect in something like a warm dark matter scenario, they should look pretty thin and regular, and kind of, to a good approximation, be kind of one-dimensional structures in this six-dimensional phase space. However, when I simulated a stream on a similar orbit, but in a cosmological cold dark matter halo, so that has a full subset of those low mass subhalos that are constantly interacting with the stream, the result looks something like this. So the overall structure of the stream remains similar because it is on the same orbit, and the stars that are that have most recently left the streams remain kind of in this thin patch of the stream. However, the rest of them have been sort of scattered off from their original orbits. And so now we see that there are density enhancements or like underdensities in the stream. It seems like some stars have been kind of completely flung out of the stream, and here the entire chunk of the stream seems to be sort of disparate from the rest of the stream. So this is basically the measurement we want to make. So this is how we want to use the stellar streams as a test of dark matter. We want to see whether stellar streams in the Milky Way look more like the top version, that are like very smooth and regular, or whether, like in the bottom, they have all of these different features that would point to past encounters of massive objects, such as dark matter subhalos orbiting the Milky Way. And as I mentioned, for a long time, all of our data on stellar streams was really coming from large imaging surveys. And so here's a footprint of really the first survey that has enabled us this very complicated view of the stellar halo. So this is a map of the Sloan Digital Sky Survey, and each pixel is a weighted number density of stars likely to be part of the halo, and the different colors correspond to the different distances. And so the Palomar 5 tidal stream that I showed earlier is here in the bottom left corner. So here's the stream, the cluster, and the stream kind of follows neatly along. But you can see that this is just one of the many structures that are present in this image. So there's a bunch of bound clusters and dwarf galaxies still surviving the halo, but the image is really dominated by this very wide stellar stream coming off from the Sagittarius dwarf galaxy. And to get back to Lam, to your point that this really, that the sort of width and the velocity dispersion in the stream corresponds to the velocity dispersion in the progenitor itself. You can see that now, because Palomar 5 is much lower mass, it produces a much thinner stream than Sagittarius, which is a dwarf galaxy, like these 3 orders of magnitude larger in mass, produces this wide stream over here. But this is not all. There are other streams, like this one over here is called the orphan stream. And you can see in width, it is between the Sagittarius and the Palomar 5. And it's called orphan because we haven't found its progenitor yet. So we think it's completely disrupted. But based on its width, we do think it's a low mass dwarf galaxy and not a globular cluster because it is wider than what we would expect for such a low mass object. And the stellar stream that I'm going to spend most of the time analyzing in this talk is called GD1 stellar stream, and it's this arc over here from bottom right to upper left. And similar to orphan stream, it doesn't have a progenitor, so we think it has been completely disrupted. So this is all that's left of that group of stars. But we do think this is actually a globular cluster stream because it is so thin and kind of reminds us of Palomar 5 stream where we do see a progenitor. And so, yeah.
That's a question. Some of these streams look so straight that it almost looks like a selection effect of some kind. Is that something that we have to worry about?
Yeah, you can see some sort of data artifacts. So the way the Sloan survey was conducted was in stripes. Basically, it was kind of the camera was staring at the sky, and like as the Earth was rotating, so they were imaging different parts of the sky. And so you can see those stripes over here, and kind of as they arc in this footprint. So those are like anything that is aligned with those stripes is then likely to be an artifact. Like for example here, like this is not a real stream over density. This is just a data artifact, or like here. But all of the streams that I mentioned actually have been confirmed as actual streams, and both with additional spectroscopic data to get their velocities and chemical abundances as well. Yeah, but it's a hard business finding stellar streams. So there, yeah, even though this has been a great improvement, having such a large area of the sky imaged in somewhat uniform way. I guess we always want to push step further and go to ever fainter stars where these selection effects become more serious. Yeah. If we want, so as I mentioned, like the experiment we want to make is measure what are the sort of density, what is the density structure along the stellar stream. And then you can imagine that those sorts of issues are also going to be very important. And so for the case of GD1, which has been a very good target because it is such a long stellar stream and also very cold. This is what a map sort of tuned to reproduce or to select stars, members of the stream, look like, and with the best data that we have until recently, basically. So this is a work from Asteri Kapasov in 2010, which then again in every pixel shows a weighted number density of stars likely to be members of the stream that is based just on their colors. And this is rotated so this is showing just sky coordinates rotated in such a way that the stream is roughly aligned with this phi2 coordinate of 0. And you can definitely see that there is an overdensity here. You can trace sort of where the stream is going, but it is much harder to assess whether any of these density variations that appear to be here, like a gap or like an overdensity, whether they're actually associated with the stream, or whether they or how much does the varying foreground from other stars in the Milky Way contribute, because even in these fields outside of the stream, you can see density variations of a similar magnitude. And so this has been, like, even though conceptually, like the problem is straightforward to define, just say, okay, measure the gaps in streams. In practice, this has been really hard to do, because just identifying members of stellar streams has been very challenging, at least if we only have colors of stars. However, as I saw on the video before, like these stellar streams or stars in a stellar stream are expected to be moving along the stream predominantly, and this is why the stream stays so cold or so narrow. So you can imagine if we had velocity information that we might get much better membership of a stellar stream by just selecting stars that are kind of moving along the stream. And so this is why, like, the last couple of years have been very exciting, because the mission from the European Space Agency called Gaia has actually provided us just that. So this is an image of the Gaia full sky. So it's a space mission. It's imaging the entire sky. Has produced a catalog of almost 2 billion stars, and here's just showing their colors and brightnesses in the galaxy. However, so this is the kind of information we had before and got the map of the GD1 as you saw. However, what we now also have is very precise measurements of velocities of stars in the galaxy as well. And so this is a visualization made by, in collaboration with Harvard graduate students Josh Spiegel and Katrin Zucker, who had taken a subset of these gas sources, calculated their distances, and to sort of get at the projected motions of stars in the plane of the sky. As you can see that, like, close to the galactic disk, the galactic plane, stars are sort of moving along the plane, which is exactly what we expect this galaxy to do. However, as we move away from the plane, more into the realm of the stellar halo, we see that the motion is more random. Except for this one location over here where there looks to be streaming motion. And this is actually the Sagittarius stream that you saw as a very prominent structure just in the density of stars in the halo. But here we can see it directly in motions of stars as well. So jitters is the most massive object, and we can just pick it out by eye in a visualization like that. What we can do is employ this information even to look at for a smaller, lower mass stellar stream, such as the GD1. And this is basically what Adrian Price-Valent, who is now a postdoc at Flatiron Institute, and I did really the day of that data became publicly available. So it was in April of 2018 where the Gaia mission released the second year of data that contained this proper motions, so projected motions of stars in the plane of the sky for those for all of their sources. And so then we were curious to see how well we can do actually. What does the GD1 stellar stream look like with this new data? And so as our first step, we kind of knew where to look. The GD1 had already been discovered and has been known since 2006. And then just selected all of the distant stars in Gaia. And this is again in those coordinates, phi1 along the stream and phi2 perpendicular to the stream. And the stream should be, again, close to phi2 of 0. And we don't see it here. However, when we look at what are the proper motions of those stars, so this is like mu phi1 is the proper motion along the stream and mu phi2 perpendicular to the stream, we can see that this distribution is now clumpy. We can see that this is the stellar halo, this is the stellar disk, and this is a small overdensity over here that turns out to be GD1 stars. It's nicely separated from the rest bulk of the galaxy. So if you only select stars in this orange box, we immediately see the stream. And this was very exciting at the time. It was the first time we could actually see the stream in individual stars. So this has not been as before. And it really just took 2 selections of the Gaia data, taking the distant stars like with a parallax smaller than 1, and this proper motion selection. However, we still, yeah.
Anna, sorry. If I look at the velocity that you plot on the right, excuse me, it looks like the velocity is primarily in the phi1 direction and not in the phi2 direction. So it's not quite along the stream, it's in fact actually perpendicular to the stream.
Oh no, so phi1 is along the coordinate along the stream. So actually having phi2 of 0 is
right.
what we would expect.
Right.
Yeah, yeah.
Fantastic.
But yeah, that's an excellent point. This is what we're looking for, exactly what we expected, and it ended up working really well. And part of why it worked so well is it's not just that we kind of know where to look and that the phi2 velocity needs to be close to 0, but also that it's at the velocities in the phi1 direction that are kind of moving in the opposite direction of everything else, all of the other stars in the galaxy. So it's kind of nicely isolated here, which helped a lot and made it possible to just see immediately the stream this way. But then we still have all of our color information from before. So if we take these stars that were now selected both in proper motions and in distance, and show the color and magnitude diagram, so color on the x-axis and magnitude on the y-axis, we see again that this is not an arbitrary random distribution of stars. So actually, like there is an overdensity over here on the left side of the distribution that kind of corresponds to what we would expect of an old and metal poor population. So if we only select that sequence, we get an even cleaner selection of GD1 stars. And so now, for comparison, like this fields outside of the stream only contain a few stars, and so they give us kind of a measure of how clean this selection is and what the contamination rate is in the stream itself. And like we got so excited when we made this plot. Immediately, like there were a couple of things that struck at us. One is that we were able to extend the length of the stream for an additional 20 degrees or so, just because now we are so much more sensitive to it. And part of the sensitivity, what it allowed to us is also to see that now that actually there are true underdensities or gaps in the stellar stream. And curiously, they're kind of looking different. This one is looking like it's completely empty, whereas this, it looks like it might have some stars that are overdense with respect to this background, or actually foreground fields of the Milky Way. So we thought that this, at the location of minus phi1 of minus 20, may be where the progenitor of the global cluster was kind of last disrupted, and it sort of cleaned out this this gap, whereas which leaves the other gap unaccounted for. But what we are, I think, most struck by is that there appear to be slight overdensities of stars outside of the mainstream. So these are, like, by eye appear slight, but when we actually calculated the probability, this is a 3 sigma enhancement of stars, and at this small stripe degree offset from the main of the stream with respect to the background. And similar, this blobby feature is more like 2.5 sigma, because the densities, the contamination is a little bit higher in this part of the stream. So now this was very exciting, because now we have the sensitivity to actually perform the test we were saying. We wanted to, there definitely is some structure in the stream, and we wanted to discover where it comes from. And other people were excited as well. So the first, late last year, there was a paper by Neil Bannock that was looking at the power spectrum of density variations. So this is, I guess, scale and degrees on the x-axis and power on the y-axis. And the measurements of the stream are shown in black data points. And they ran some simulations first of old stellar stream just orbiting in a galaxy with baryonic structures like spiral arms and molecular clouds in the Milky Way disk, and got the power that is much lower than observed. However, when they added a population of cold dark matter subhalos to their simulation, they found that the amount of structure produced in the simulation is comparable to what is observed in the data. So the title of that paper was Evidence of a Population of Dark Subhalos from Gaia and Pan-STARRS Observations of the GD1 Stream. So that was very exciting, which looks like statistically, some of those gaps should be caused by an encounter of a dark matter subhalo. However, more recently, there was another paper from Rodrigo Ibata's group that performed a similar analysis. So they have a slightly different selection of the solar stream, and so the data on this panel is shown in yellow. But again, as before, on the x-axis shows the scale in degrees, and the y-axis shows the power. You can see that there is some amount of clunkiness that they measure in the stream, but what they find is that if they produce a more realistic simulation, like an n-body simulation that realistically takes into account the variations in density expected from the way stars leave the cluster, you can get similar amounts of density variations in this way. So the title of this paper was Detection of Strong Epicyclic Density Spikes in the GD1 Stellar Stream, an absence of evidence for the influence of dark matter subhalos, with the question mark. So
Sorry,
this is,
can I
yeah?
ask you a few questions about these very interesting plots?
Yeah.
First of all, on the y-axis, when it's plot power, this is the power spectrum of fluctuations, basically in density along the.
Yes.
Is that what it is?
Yes. Yes. That's a perspective in fluctuations of the density. Yeah, at different scales. Yeah.
And can I read it as a dimensionless thing? Meaning, if the power is 1, it means basically I have order 1 fluctuations on that scale. Is that the way I should read it, or I should be more careful about units probably?
Yeah, I'm not sure myself. I did notice that the data is not on the same exactly the same location between these two studies. So I'm not exactly sure that that's the if maybe more care is needed. But if we look back over here, so these are the
Yeah.
kind of like they're like these, like this is kind of an overdensity, this is an underdensity, this is again an underdensity, overdensity, underdensity, overdensity. Those are significant variations. So it might be that even order unity would be the correct kind of amplitude.
Yeah.
Yeah.
And for the plot on the right, so the color band, the higher one, that is data, and the black band, that is from n-body simulation. So the interpretation is that these density fluctuations cannot be accounted for by subhalos, but it has to be accounted for some other way. That's the interpretation.
Yeah, they just say that, so they didn't say that it cannot be the subhalos. They just said that part of that variation, or a large part of that variation, could be attributed to internal processes in the cluster itself.
I see.
Yeah, so they're just kind of saying that not all, like that there are like different ways to introduce structure in clusters, and dark matters or like in stellar streams, and the dark matter subhalos are not the only one that is relevant here.
So the hypothesis, I don't know whether they actually have a hypothesis. The hypothesis is that these fluctuation in density is intrinsic to the production of these streams out of the globular cluster, rather than scattering by whatever, molecular cloud.
Yeah, exactly. And I can go back to this plot over here. So it's it's a little bit hard to see, I guess, in this particular example, but you can see there are like slight kinks in this model, and they sort of look like, or they are due to the epicyclic motion of stars around, like in the stream around the orbit of the progenitor. So what the stream stars are on slightly different orbits that sort of epicycle around the orbit of the cluster. And then in those locations where they kind of epicycles, like in projection, they can appear overdense. I guess in this case, it depends a little bit on the mass of the cluster, how pronounced those are. And so here they're not pronounced as much, but it's Rodrigo Ibata and his group are showing that you can find properties of the progenitor that would produce stronger variations. So this is, yeah, what they're saying, strong epicyclic density spikes that would that could explain at least part of those variations in the data.
Thanks.
Yeah. So there was kind of showing how it's there are like many things that happening here, and it's just interpreting or like finding the gaps in the stream is not enough, but it also kind of this image of GD1, like that shows very prominent gaps was very exciting, because I have them, but we're I was personally curious to see whether we can explain these off-stream features like the spur and the blob and what they might be telling us, whether they would be able to break this sort of degeneracy between the external perturbations to the stream to produce the gaps or some internal processes. And as we were, as Adrian and I were making those early plots of GD1, Catherine Johnson was in the room and she remembered that in some cases, you can get features like that following an encounter. And so we then went back to this Yoon et al. Study from 2011, which simulated global clusters like Palomar 5 and sort of bombarded them with one dark matter subhalo. And so the location of this impact is shown as a gray cross. And then the different panels are just different variations of the orbit and time since the encounter. So you can see that in most cases, like this encounter is associated with a gap, sometimes more or less prominent. But in a couple of cases, here in the middle row, the right panel, looks like the whole stream has been folded. So that is, while most of the stars are still in the mainstream, there are some that are offset from it and the structure that kind of looks like the spur that we saw in GD1. And similarly in this bottom row, middle panel, there is like this, something that looks kind of like the spur. And so this is a finding already almost 10 years ago. However, much of the community has really focused on understanding what the gaps themselves tell us about dark matter subhalos, because they were present in every situation that happens. And so there has been a lot of theoretical work, and this is probably just a partial listing of all of the relevant references. But the offshoot was that we have a pretty good understanding of how the gaps in streams change as a function of velocity, relative velocity between the stream and the subhalo. So as you might expect, the slower moving subhalos would produce larger gaps. And similarly for the impact parameter in the bottom row here, the closer the subhalo comes upstream, the larger the gap again. And also for the mass, the more massive the subhalo, the larger the gap as well. However, we don't have any handle on what structures like the spur would be telling us. And so last year I did sort of a preliminary study of the parameter space of trying to match, to create a model of GD1 encountering a massive object and to see if we can actually reproduce the observed structure of the stream. So here is our best guess at what happened. So a stream like GD1 orbiting the galaxy half a billion years ago encounters a massive object that gives a velocity kick to some of the stars closest to the impact. And so those stars now sort of are in a ring around the mainstream and sort of precess around it. And at the present, viewed in projection, they appear like this spur of stars. And once we project this model onto the sky coordinates, it looks very similar to the data. So we reproduce this one gap by disrupting the globular cluster progenitor here, and this other by having an encounter like half or 500 million years ago by a massive object, like a few 5 million solar masses that's very compact and moving, coming pretty close to the stream and moving at sort of typical halo velocity. And so in this model, we were very excited because it matches the location and the size of the gap, and also the kind of extent and the separation of the spur of stars as we have observed in the data itself that is shown on the top here. And like cosmologically, this object is in this interesting mass regime that, if indeed it can be attributed to dark matter, this would really rule out many of the warm dark matter models that are still allowed. However, this is only one such example, and we try to do a preliminary search of the parameter space to see what range of these parameters are allowed and produce a similar morphology to this one, so that they both have the gap and the spur of stars. So we varied all of these 5 parameters, but for brevity, I'll just show the findings or our constraints on the mass on the y-axis and the size on the x-axis of this GD1 perturber. So an object that introduced a gap and a spur in the GD1 stellar stream. So this is shown here in the gray shaded area. And then just for comparison, now we're showing some other possible objects that might have encountered the stream in the galaxy. So the molecular clouds and in the outer disk are shown as circles, dwarf galaxies are shown as squares, and globular clusters are shown as triangles. The dark matter subhalos would lie in this band. So this is an expected relation between the size and mass of lambda CDM subhalos, and the dotted lines are showing the 1, 2, and 3 sigma scatter. So you can see that the overlap here is fairly small, and it's kind of, it would be an unusual lambda CDM subhalo if that's what happened. And at face value, I see like, okay, there is the largest overlap here with the population of globular clusters. However, those can be ruled out based on their orbits. So since now with the Gaia information, we also have the motions of all of the globular clusters and can integrate their orbits back and see if ever they came close to the GD1 stellar stream or that location in the stellar stream, and it turns out that the answer is not really. And similar for the dwarf galaxies and also for the molecular clouds. So this now leaves us with this kind of very empty looking plot, and yet something happened. We're pretty certain that the spur is associated with the stream, and so our possibilities are that it is an unseen globular cluster that is kind of hiding maybe behind the bulk of the Milky Way. It could be an unusual dark matter subhalo. Also, you'll know that these kind of contour, the shaded region, continues outside of the plot to more compact sizes. So our models are completely happy to have something like a point mass or supermassive black hole be the culprit. It's kind of hard, I think, astrophysically to justify its presence in the halo, but we're kind of going at it with an open mind, and we're hoping that with further data we can predict where the progenitor or like this perturber should be in the galaxy, and then just go look at it. If it is a globular cluster, we should be able to detect it. If there's a dark matter subhalo, we might observe it in lensing, and there might be some other signatures of like an X-ray of a supermassive black hole. So we're then pretty excited. So like, okay, let's try doing this experiment. Let's take all of this model that are within this gray shaded region, like all on different orbits that have encountered the model GD1 stream and produce the gap and the spur of the right size and shape, and ask where would those objects be today, and got basically this. So they could be anywhere in the sky. So this is not quite the localization we were looking for, but thankfully the model is predictive. So we can color code this by the expected difference in radial velocity between the stream and the spur. And you can see now that there is some structure. It is very small, so the scale on the color bar goes from -5 to +5 kilometers a second. So we need fairly precise data, but it kind of points one way to constrain the to further narrow down where we should be looking for the perturber of GD1. And so,
Anna,
yes,
this is very interesting. Could you go to the plot before this one?
this one?
Yeah. I guess I have two questions. One is, we can see from your gray contour that there is some kind of bound, you know, the perturber cannot be too light, which is understandable because if it's too light, then that's not much. It cannot be too massive either. And I wonder if I have a very massive perturber, but I put it out to larger impact parameter, wouldn't be able to accommodate a more massive perturber. Why is there an upper bound on the mass?
Yeah, that's an interesting interesting question, and it kind of at least in our model, what we were finding is that to have the spur of stars be distinct from the stellar stream, so removed a little bit, like by a degree or so, that already implies that the impact was fairly recent. So in our models, it turned out that if the impact happened long ago, that then the spur would be more aligned with the stream, and we wouldn't like see it as a separate spur. And so the way this kind of plays in is that if you have a more massive perturber that happened that was farther away, would have to it will take a different time to create the gap of the same size. And so it kind of works out that it wouldn't create both the gap of the right size and the spur of the right separation. So I think this is why we are getting part of this upper bound.
I see.
Yeah.
I see. And the other question I have is regarding this lambda CDM subhalo, that the other gray band. The band span, you know, some range in mass and size. Does that range account for the fact that these lambda CDM subhalos would be tidal strip themselves inside Milky Way? Is that account?
Yeah, exactly. That is, so this is why we use this particular study of Moulinet from 2017, because they actually measured this mass size relation in different parts of the galaxy where a different amount of tidal stripping happened. So what we use here is for in the range between 10 or like 15 and 30 kiloparsecs from the galactic center where GD1 orbits. And indeed, like those, so that whole relation then is shifted to more compact sizes with respect to the lambda CDM halos themselves that are not tidally stripped. They are the relation is then shifted to the right, but in order to survive these subhalos, these radii have to be more compact. So this is why the band is over here. Yeah.
Thank you.
Yeah. No, that's a very good point. And still, like, even if those are kind of the more compact ones that are surviving, it looks like it's kind of not getting all the way to our preferred location. But yeah, we were actually hoping then to be able to say a little bit more if we measure radial velocities. And so here is the view of the stream zoomed in on this gap at minus 40 degrees and the spur coming out of it. And the literature data is shown in blue. So these are the blue stars are the radial velocity measurements. And you can see that they're only in the mainstream. And what we are interested in is actually measuring the difference between the radial velocity in the mainstream and the spur. So I went to the MMT telescope and used the hectoshells instrument to measure radial velocities in these 8 fields. So we measured 4 locations in the mainstream, and those are shown in light orange, and then the 4 locations in the spur shown in dark orange. And interestingly, we found very little difference in radial velocities at these locations that we have parallel fields both in the spur and in the mainstream. And so the bottom panel is showing the radial velocity offset from the best fitting orbit. So you can see that it's like very, very well defined and looks like very similar between those 2 structures. And even if we zoom in this plus or minus 5 kilometers a second range, you can see that they're like within 1 kilometer a second is the difference between the spur and the stream, and kind of well within the uncertainties here. So if we go back to our figure here and then just limit ourselves to models that produce radial velocities of difference between the stream and the spur of plus or minus 1 kilometer a second, we are left with these set of models. So you can see now that there's still like a number of models that and on different orbits that can produce the right morphology and the right kinematics as we observed in GD1, but most of them are sort of confined to this one location or kind of one great circle on the sky, and that was really exciting because it sort of opens up the possibility that we actually might be able to go directly search for individual objects in the Milky Way halo, individual clumps of dark matter, and sort of in the very optimistic case that we find something that would actually then enable us a multi-messenger view of dark matter, where we have its effects measured gravitationally on solar streams and maybe observed directly since we know where to look for it. So there's one, like the first exciting finding of getting precise radial velocities in such a cold stellar stream, where we actually can resolve like these differences of 1 kilometer a second. I would like to end like with a couple of more possibilities of like what else we could do with this data. And it'd be remiss not to mention this study by Nicola Morisco and Avi Loeb from a couple of years ago, where they actually simulated what a stellar stream would look like in a fuzzy dark matter scenario. And so on the left, they're showing a simulated stream in a completely smooth halo. So I guess their parameter is that the axion mass of the fuzzy dark matter particle is then infinite, so it's completely smooth. And then the top panel is showing the top-down view of the stellar stream, and those epicyclic overdensities I mentioned before, those are the clumps you can see here. On the bottom is the sort of profile or in-plane view of the stellar stream, and you can see that it's fairly thin, and that striping again are those epicycles. However, in the case where the fuzzy dark matter particle is less massive, something like 2 times 10 to the minus 22 electron volts, the stream becomes dynamically heated by all the quantum fluctuations that are happening on galactic scales or kind of kiloparsec scales that the stream is encountering. And so this translates then to this more heated looking profile of a vertical profile of a stellar stream. And what I'm very excited about now and I'm working on with a summer student on is actually measuring the velocity dispersion in the GD1 stellar stream in the data that we showed before. And some preliminary results show that there is some evidence for dynamical heating. So we're measuring velocity dispersion that is something like 2 kilometers a second, whereas Megan's, like the summer students, models are showing that a stream on that orbit, like for a range of masses, should have velocity dispersions that are smaller than 1 kilometer a second in the smooth case. So this is sort of another avenue that is becoming possible of how to test the nature of dark matter with stellar streams. And I just wanted to end with, yeah.
Would CDM substructure, just subhalos, do the same thing? Would they also cause this basically over time, basically dynamical heating of the stellar streams, or even molecular clouds and things?
Yeah, they would. So that is, yeah, what we now can say that it looks like something. There is evidence for heating, but yeah, you're exactly right. This is this is the only theoretical study that has looked into this question. So it's unclear what would be a unique measure. What we are hoping for is to simulate this more realistically for the stream on a GD1-like orbit, and in principle, like I think different streams should be differently susceptible to those effects. For example, GD1 in particular is fairly resilient to molecular clouds because it crosses the disk very far away from the galaxy, where there is really not many molecular clouds left. And so, and I think that the quantum fluctuations should be more prominent closer to the galactic center, whereas the dark matter subhalos should be tidally disrupted closer to the galactic center. So maybe with one stream, it will be hard to distinguish like where this heating is coming from, but with a combination of streams that are orbiting at different distances from the galaxy, I'm hopeful that we actually will be able to disentangle all of these kind of sources of heating in the galaxy. And this is kind of where I wanted to end with my last slide, is kind of saying that most of the results that I've shown here really are coming from one single stream. But we know something like 60 stellar streams in the Milky Way, and we've studied this one because it's such a good and easy target because it's so nearby and we have a lot of data on it. But just to kind of tease a little bit what we can expect in the future, I'm showing a visualization of a simulated set of stellar streams, kind of observed at the SDSS kind of level. As you can see, and they're color coded by their distance. So you can see that most of the ones that we can see with this data that we now have at hand are kind of nearby within 10 kiloparsecs or so. However, as we get better and better data, so showing the limiting magnitude of the survey until we reach LSST 10-year depth, we get a much more fleshed out picture of the stellar halo. So the nearby streams are like observed in a lot more detail, and then we see many stellar streams even farther out in the halo, all the way out to beyond 100 kiloparsecs. So this really, I think there is a lot to be done with the streams that we already have. And also there's a lot of excitement to come from all the new discoveries of streams, especially in the outer halo. That should be like very unique test of dark matter physics overall. So this is my last slide. So again.
Well, thank you very much, Anna. This is fantastic. I already asked a lot of questions, but I have quite a few more. I don't know how much time you have though, because you said you have to go.
Yeah. I forgot to get a clock, like watch, so I don't actually know what time it is.
We have gone on for an hour or maybe even a little bit more, but I think it's okay. It's all recorded.
Okay.
Do you have a few minutes? I can ask you a few more questions.
Yeah.
This is very nice. One question I had was when you talk about the spur, or people talk about the gaps, or these groups that publish results based on the power spectrum, mostly the focus is on the density structure. You know, sometimes they are very low density and sometimes they're high density, or just the statistical density fluctuations thereof. In addition, the data, of course, has velocity information. In particular, for example, just from Gaia alone, you have proper motion. And so there should be something about the velocity structure or the velocity fluctuation that you can also use, no? Is that something that has been explored or being explored?
Yeah, pretty much. So we're of course very excited about the next data release from Gaia, which is going to happen in, I think, half a year. It's it's probably delayed a little bit because of the pandemic. But even so you saw that like the velocity precision we need, like for the structure is really on small kind of velocity scales on the order of kilometers a second. So even like future Gaia data, it'll be hard to distinguish that. However, we propose and now obtained the first epoch for precise HST proper motions. Of course, we can now with HST we can achieve those the precision we need to be comparable to the radial velocity precision we have, but it's over a much smaller field. So it's going to there's only like a few locations in the stream that we are monitoring, and so we got the first epoch, and in a couple of years we'll get the second epoch imaging to measure those precise proper motions. But yeah, that's definitely something we have going on, and any future cosmological surveys I think could really bring a lot to the Milky Way science if they are scheduled in such a way that proper motions can be measured kind of precisely.
Can you give us an idea currently with Gaia? What is the precision in velocity in the proper motion?
It's, oh gosh, I guess it depends a lot. It depends on distance, right? So I guess I can show here. So the proper motion box that sort of we selected was like 4 milliarc seconds per year wide. I think that would be like kind of 10 kilometers a second at the distance of GD1, but I'm
okay.
Yeah.
Okay.
We kind of or order of magnitude. Yeah.
Yes. The other question I had was, you showed this very nice plot where you can actually even predict where the perturber is.
Mm-hmm.
And by focusing on a radial velocity dispersion that's sufficiently small, somehow you pick out this kind of lower left
Mm-hmm. Yeah.
corner. And I wonder, what is it about that constraint that pick out that particular corner? Does it have to do with the orbit of the globular cluster that you know to have that velocity, delta V of R less than 1 kilometer per second?
Mm-hmm.
The encounter must be fairly recent or something like that. What is it that actually picks out that location?
Yeah, that's an excellent question, and I don't have a principled answer to it yet. So this is uh, just a very kind of quick result that we wanted to report on the really small velocity difference, and kind of that definitively associates the spur with the stream, and then just went back to our earlier models and looked which fit. And so we just shown that, and kind of as a proof of principle that we might localize the stream on the sky, but haven't done the more principled study of why it's at this particular location. As you saw in the movie, after the encounter like that, okay, I can play it again, like this, like the stars that are pulled out of the stream, they're kind of or precessing around the orbit. So it really is at this location, it looks like the spur is pointing a one way, or like there are two spurs, and like in some projection it looks like they're going in different ways. So certainly that matters. That somehow that translates to the, like, we combined with the timing to constrain the orbit on the sky, but we don't really have a good sort of analytic explanation, even though it looks like there should be one, because it looks like that's what's happening. And yeah, okay.
That's interesting. And when you plot that the predicted location, that is the predicted location of the encounter, right? Of the perturber when the closest encounter happens.
Oh no, this is where the perturber would be today. So taking it, so
nice.
yeah,
Nice.
so those are the encounter position. That's a parameter. Now we then forward that to the future, to the present day. Yeah.
I see. Very nice. Very nice. Maybe one last question, if you'll bear with me. This is all fascinating. One thing I noticed in terms of how to use these density fluctuations along the stream, in some sense, there are kind of two kind of distinct approach. One is kind of statistical. You measure the power spectrum of fluctuations.
Yep.
The other is like what you have been showing us, to focus on particular features like the spur or this gap and so on. It reminds me of a lot of what actually we do also in large-scale structure. There's the statistical approach, measuring power spectrum and so on. And then there's the approach of focusing on individual objects like, galaxy clusters and so on. Perhaps there is something kind of like maybe in between, in the sense that what is going on is that these kind of isolated features, they are so distinct that of course we want to focus on them. And that's really telling you that at some level, the fluctuations are very non-Gaussian. Therefore, even from a pure statistics point of view, probably there's something to be gained beyond just measuring the power spectrum, which is a 2-point statistics.
Mm-hmm.
One might want to go into basically non-Gaussian statistics, meaning measuring not just the 2-point function or the second moment, measure the third moment or fourth moment of the density fluctuations. Because presumably the density fluctuations, if you plot it, some probability is actually very non-Gaussian with long tail.
Right.
And it might, even from the point of view of just measuring statistics, there might be something to be gained by going beyond just a second order statistics.
Oh, that's really interesting point. And yeah, I remember from attending the large scale structure talks that now that's a really big field, like doing the 3 or 4-point statistics and seeing. So it would be interesting, yeah, to see if like that could distinguish, even if the
Right.
say 2-point statistics are sort of degenerate between like the influence of CDM or internal effects of the cluster, maybe like the 3-point statistics
Exactly.
would be different. Yeah, that's a very interesting point.
For example, if the encounter come from kind of isolated, very compact perturbers, probably it would be more non-Gaussian, I'm guessing, because it's kind of isolated, relatively rare encounters, versus if I have kind of lots of small, more diffuse encounters, or I could do something that's more Gaussian. Okay? So there will be some way of the, so, and I'm guessing maybe one helpful thing to just plot. I don't know whether that has ever been plotted. It's, let's say, this power spectrum is measure of kind of the second moment of the density perturbations, right, along the stream. Now, suppose I just plot the probability. I just say, let's plot a histogram of probability as a function of density perturbations along the stream. Does that probability distribution, how does it look? Does it look Gaussian? Does it look like a long tail? Just actually seeing it might be a helpful first step just to see what it looks like. Probably at the moment it might be a little bit noisy, but I think just seeing it would be a helpful thing to as kind of a first step.
Yeah, that's a great idea, and I wrote it down, so I'll be sure to let you know. I think it is.
I'll be very interested.
I think this is like to really a high degree, high purity sample of stars. So when we targeted, like all of our top priority targets, which are the ones shown here, ended up being radial velocity members, or like most of them. So yeah, I think it might be actually fairly straightforward to do this.
That's great.
To do this calculation. Yeah, that's a great point.
Since we are able to see by eye so easily these features, I'm guessing that histogram must be fairly non-Gaussian.
Yeah.
It would be interesting to see,
No, that's a great point, and yeah, because ultimately, yeah, this is there should be a population of, like in some models, there should be a population of subhalos, and we don't want to just do the study on one, because I guess we could have gotten unlucky and it could have been like a black hole.
Well, in the end, I think both approaches are actually useful. We do both kind of things. Yeah, that's what we do in cosmology.
Yeah. Oh, it's should be. Well, I'm really glad that we got paired and that you made the suggestion. I'm really excited to try it out.
Right. Well, this is super nice, Anna. This is very, very helpful and informative.
Oh, I'm glad, and thank you for being such a wonderful host and having such a large number of insightful questions.
Right. So I guess I'll see you next week.
Sounds good. I'll see you next week.
All right.
I will. Okay, I'll stop recording.